All right, so today we are talking about curve sketching with rational functions. When I say the word rational functions, what should come to mind is any function that can be written as a fraction where you have a variable in the denominator. So we have to find critical values and different characteristics of the equation that will help us sketch the curve without using the calculator. So anytime we have a rational function, one of the very first things you should always ask yourself is if you have any vertical asymptotes or holes. Now, those are two different values that look different on the graph, but both come from the denominator being undefined. So if I'm looking for a vertical asymptote, vertical asymptotes occur when the denominator is equal to 0 and it cannot be reduced. All right, so basically, if I look at this and I see a variable in the denominator, I set the denominator equal to 0. So this is me finding my vertical asymptote. X plus 1 equal to 0. I minus 1 over. I get x equals -1. And what do I mean by it cannot be reduced? There was nothing that I could factor up top, and there's nothing I could factor on the bottom. So I'm looking here. I can't cross this out. So therefore, since it cannot be reduced, this x equals -1, that makes this denominator undefined, will be an asymptote. Okay? Holes occur also when the denominator is, when you have a value that makes the denominator equal to 0, but it also is able to be reduced and can be reduced. So we don't have any holes here. However, what if I gave you an equation that looked like this? Y equals x squared minus 25 over x minus 5. If I gave you this equation, you would say, oh, I definitely have some undefined value when x equals 5 because I set the denominator equal to 0 and I got x equals 5. And now I want to decide, is this a vertical asymptote or is it a hole? It's one or the other. Well, here I look at the numerator, I go, wait a minute, I think I can factor this and reduce it. So the numerator becomes x plus 5, it's dot, x minus 5. So I'm just rewriting the function, and I have the original denominator is x minus 5 in the bottom. Now, I already said that x equals 5 is what's going to make this denominator equal to 0. However, this reduces, and this isn't the first time we've seen holes. I'm just kind of reminding you this. So if I see that this is reduced, that means that the value 5, when x is 5, is the x coordinate of the hole. To find the y coordinate, you would take that x value and plug it into the reduced version. After I cross this out, I get the equation y equals x plus 5 over 1, because that crossed out. And then you plug in the 5, and I would get that y would equal 10, and that would be the hole. So these are two values you are going to be asked to find when we curve sketch any rational function. So vertical asymptotes, you set the denominator equal to 0, you get a value that denominator can't be reduced, so that's going to be an asymptote. On a graph, you will see at -1 a vertical asymptote. Here, if you're able to reduce it on the graph, you're going to go to wherever 5, 10 is and create a hole. Okay? All right, the next part is the question of horizontal asymptotes. Horizontal asymptotes, if I'd like to make you envision it first before we go ahead and algebraically solve for them. Horizontal asymptotes look like this. If I have a graph, and I know that you guys are aware of vertical asymptotes up and down, but a horizontal asymptote would be something that looks like this. And that towards the graph, as I go to all the way to the right, heads to that horizontal asymptote. Or if I go all the way to the left, the graph tends towards this value. Let's say this value is 1. My vertical asymptote here would be x equals 1. Now this is not the graph of this function. I'm just showing you what a horizontal asymptote is. So what is being seen is that as the graph goes all the way to the right, or another way to say that is positive infinity, as this graph approaches positive infinity, it goes to a certain y value, or as the graph goes to negative infinity, it goes to a certain y value. So that means that horizontal asymptotes are found as we study the graph as it approaches infinity. Well, anytime I'm studying a graph when it approaches a certain number, I'm talking to you about a limit. So horizontal asymptotes are found by testing the limit at infinity. And we talked about limits at infinity already. There was 3 scenarios. When we have limits at infinity, I'm going, what's happening as x approaches positive infinity or negative infinity for f of x? There was 3 scenarios. Your first scenario was, is the function top-heavy? And top-heavy means that the numerator has the largest degree. So for example, if you had y equals x to the 5th over x to the 5th, let's say, plus 3x over x minus x squared. Well, the largest exponent in the numerator is 5, and the largest exponent in the denominator is 2. Well, which one's the largest out of the 2 is at the top. This is considered top-heavy. Well, if it's top-heavy, we know the limit to any function that's top-heavy as it approaches negative infinity or positive infinity is going to be either infinity or negative infinity. That means that it's going to be shooting all the way up or all the way down. So it's not going to go to any specific y value. Therefore, if you have a top-heavy function, and I'm asking you about horizontal asymptotes, there are no horizontal asymptotes. None. Okay, well, what if it was bottom-heavy? Well, if we had a function that's bottom-heavy, that means that the largest degree is on the bottom. So for example, y equals 5 over x squared, or 5x over x squared. If you look at that, my denominator has the largest degree. So we know the limit as x approaches infinity or negative infinity for a bottom-heavy would equal 0. So therefore, if I have a bottom-heavy function, the horizontal asymptote will be not just 0, y equals 0. I would be drawing a dotted line representing a horizontal asymptote along the x-axis because that is the y equals 0. All right, last but not least is if it was equal. If the degrees were equal. So if I had a function that looked like this, y equals 3x minus 5x squared over 3x squared minus 2. Well, my largest degree in the numerator is 2, and the largest degree in the denominator is 2. They're equal. So we said the limit was just the division of the coefficient. The coefficient is negative 5 and 3. So therefore, the limit to this function to infinity or negative infinity for the function 3x minus 5x squared over 3x squared minus 2 would equal negative 5/3. But when we're talking about a horizontal asymptote, it's the equation y equals negative 5/3. Okay, so now let's do this problem. If I have this function here, I want to know, does it have any horizontal asymptotes? So we know we have to ask ourselves, is this top-heavy, bottom-heavy, or equal? So here I look and I go, the largest exponent on this function on the numerator is 1, and the largest exponent on the denominator is 1. So I have the scenario where we have an equal degree. And since we have an equal degree, we just take the division of the coefficients. Well, the coefficient here is 1, so it's just 2 divided by 1, which is just 2. The horizontal asymptote, and we're just going to say HA, is y equals 2. Perfect. Okay, now to the next piece. These two you should know, okay, x-intercept and y-intercept. X-intercept you should have down already in your notes from the last video, set y equal to 0. Y-intercept set x equal to 0. Okay, so if I'm sitting here and I take a rational function, 2x minus 1 over x plus 1, and set y equal to 0, I'm setting a rational function equal to 0. Now guys, you can just put this over 1 and cross multiply and you'll see that the denominator goes away. But you should know that a rational function is only going to equal 0 if the numerator equals 0. So either way, however you want to look at it, I get 2x minus 1 times 1 is equal to 0 times x plus 1, which is just 0. So then when I add this, I just get 2x equals 1, so x equals 1/2. So my x-intercept is 1/2, comma 0. All right, here, y-intercepts, you're just setting x equal to 0. So I always have it in my head, whatever intercept I'm looking for, I'm setting the other variable equal to 0. So I'm just going to take 2, and wherever I see the x, I'm going to take the x out, and I'm going to set x equal to 0 and find the y-intercept. So I just get -1 over 1 is equal to y, so it's -1 is the y-intercept. So the point is 0, comma, -1. Okay, great. Next, we're going to be asked max and mins. Well, this at this point should be ringing a bell. Anything with a maximum or a minimum, I'm going to talk about, and hopefully you're saying this before I say it, the first derivative. Okay, I'm looking for the first derivative to be set equal to 0, or the first derivative to be undefined. And there's a little thing about asymptotes. We know we have an asymptote here at x equals -1. All right, so asymptotes are hereditary. If I take the derivative of this, I'm still going to have an asymptote at -1. So I know I have a critical value at -1 already. But if you don't pick that up, that's fine, because after you do your first derivative, you're going to be able to find that. So let's get to do the work, okay? Taking the first derivative. If I'm taking the first derivative, I'm going to use quotient rule. So I'm going to say dy dx is equal to the derivative of the upper, the first, is just 2, times the second, minus the derivative of the second, which is 1, times the first. And don't forget that you have this box here over the second squared. Okay, so now let's clean it up. Up top here, I get 2x plus 2. I'm just distributing that. And here, guys, I'm going to take that -1 and distribute it to both and get -2x plus 1. Just so you don't get confused with my notation, I'm just going to take this number line out. Okay, so now when I go ahead and combine, the 2x's cross out, and 2 plus 1, I get 3 over x plus 1 squared. That's my first derivative. Okay, so now first derivative undefined. I already knew that it's going to be x equals -1, but say you're not sure, you look at this and you go, yeah, the first derivative can be undefined if the denominator is equal to 0. So I square root, x plus 1 equals 0, x equals -1. So a critical value on my first derivative line, I'm going to put -1, and I'm going to go ahead and do a dotted line there. Okay, and then here I'm looking for if the first derivative can ever equal 0. Well, if I have this 3 over x plus 1 squared and set equal to 0, if I cross multiply this, I get 3 equals 0, which is not true. There's no more critical values. So that's it. So now it's just up to me to pick a number to the left and to the right to see about having a possible max or min. I'm just going to pause that and start the next video. But at this point, I want you to go ahead and do the first derivative test and try it.